Let me check if it's okay. Okay, guys. So no one's present. It's been the story for the last few days. But anyways, so um, I welcome you all to this week 11 problem solving or doubt clearing session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor N.P. Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma. I am a TA for this course and I'm a PMRF scholar at IIT Kanpur. So, so whatever we have been doing with this course, right? We what we wanted to take from this course was how are we going to build intelligent and smarter grids given the fact that we want to increase we want to increase renewable generation while simultaneously decreasing the reliance over fossil fuels. And what we want to do is we want to make sure that the the amount of energy we are that the amount of energy that we are producing is being efficiently delivered across the channels, right? And for this, we are taking leaps and we are developing smarter grids, which take the advantages of the communication protocol, the interoperability, and they use that to increase efficiency, enhance reliability, and increase the resiliency of the system, right? So that is what we want to do. And now, after going through everything, now we have what we have been doing from the past few lectures is we are demonstrating, right? So to give you a glimpse of how the things are being developed in real life, right? In real world, how do you make the systems intelligent? How are you making AC/DC microgrids, setting up AC/DC microgrids, and stuff like that? And we will be continuing our discussion in the same way. And we'll first start with the energy management schemes or power flow control strategies. Then we won't go through the demonstration because I have not done that, so I'm not in a position to tell you all about it. But yeah, the videos are self-explanatory if you have been through the lectures, and but we will be discussing all about the stuff that the instructor has talked about in the course, right? So that is something that we'll definitely do. And let's start the lecture. So I'll just quickly share my screen. Okay, just a second. Let me keep this up. Hmm. Okay, so the first thing that we'll discuss today is the energy management scheme and the control scheme and how DC microgrids are being developed, right? So last class we discussed about a crucial aspect of the AC microgrids, that is the coordinated voltage control schemes, right? And we today move towards the DC microgrid structure and AC/DC microgrid structure, and we'll talk about various different components and how are they modeled, and what are the energy management schemes or power flow control strategy in those energy management schemes, right? So this right here is a structure that we have been talking about going through from a very long time, right? We know if there is a solar panel connected, we use a boost converter which is coupled to a DC bus. So it's a DC microgrid. So you have a DC bus. And what you want to do is you want to make sure that your load and generation and the power exchange from the grid is able to meet A, the load, and B, able to keep the voltage at the reference bus, voltage of the DC bus at a reference value, whichever is the norm of that, right? So what we use is for solar panels, we have the boost converter. For battery, we use a single H-bridge bidirectional converter. For ultra capacitor, also we use single H-bridge bidirectional converter. And this topology of this H-bridge converters we have already went through. We use them because they have an isolation, and this isolation helps us to make sure when exchanging power with the grid, when we are consuming or when we are giving out, we don't we are isolating ourselves from the disturbances in the grid and isolating the grid from the disturbances in the ultra capacitor or the battery energy storage systems in general, right? Similarly, just a second. हेलो हेलो हाँ सर मैं आपको 2 घंटे बाद फ़ोन करूँ मेरी क्लास है एनपीटीएल की मैं वो ले रहा था हम्म हम्म राइट सॉरी फॉर दैट आई होप आई एम ऑडिबल राइट so yeah. And the same way, we have a full H-bridge bidirectional AC-DC converter. So we want to make sure that the AC utility grid is connected to the DC bus using this AC-DC bidirectional converter. And again, we have isolations, and this isolation helps us in, making sure that the transients don't travel. Hmm. All right. So now I have discussed this before. I mean, this is something that we have been discussing for quite a long time. But if I just a second. Hmm. But let's say if I want to talk to you about why energy management scheme, what's the need of it, or why a power flow control strategy. So we know that we have various different DERs, right? These batteries, these PV panels, these everything that is connected to the grid or anywhere is something that can be controlled, right? The power output or input to that DER or that generator can be controlled using this using can be controlled, right? And how can we provide a control over that? It's through using an energy management scheme, which in itself has a power flow control strategy, which makes sure that how the power is flowing from various different devices, right? And that is what the purpose of PFC is, or power flow control strategies. We'll come to the power flow control strategy in a bit, but I just wanted to talk about that before we move further. But now, one interesting question that I can ask from all of you guys is, and I hope that you are able to answer this too, because this is something that we have dealt with for quite some time now, right? And that is why DC microgrids are now coming into the picture. DC microgrids are not that prevalent, so you won't see in real life them being implemented so soon. Why is that? Is because we don't have matured technology, or we don't have matured operations, a guide for their operation, right? We don't have that at this point of time. Why is that? Is because they are a fairly newer microgrids that are coming into the picture, and their evolution is only because of the fact that the DERs that we have at the distribution side, they all produce energy in DC, right? And for that, to make sure that we extract that and be useful for our AC utility purposes, we use an extra convergence stage, and that convergence stage is in the form of inverters. So because they have the benefits associated with them, we are now looking forward to them. But the technology has not matured yet. So let's say, for example, we don't have enough standards that govern how much reference voltage can they have. Like for example, we know for an AC microgrid, if it's single phase, it's 240 volts for us, and if it's three phase, it's 410 volts, right? But what about these DC microgrids? So you will see 15 volts, 48 volts, 500 volts. There's no standardization across these architecture, different types of architecture, right? And also they don't have developed protection schemes. So like for example, we discussed a few protection schemes, right? And they are all applicable to AC microgrids, not DC microgrids. And we are now currently, so why is that? Because the short circuit current is different, the way that travels from device to device is different, and that is why we need to make sure that we are developing. Just a second, it's being recorded, right? Yeah, I have to check, I'm sorry. So yeah, so now they are being developed, and we discussed a few of these protection schemes for DC microgrids, and we talked about how non-detection zone creeps in and what does non-detection zones, right? If you are not familiar with them, no worries, please go back to our week, I guess 5, 6, 7, between those. We discussed in depth about these protection schemes, and you'll be able to appreciate, right? But but I know I just discussed, but let me just write down these advantages, right? So that if you want to take a look at, you can, right? What are the advantages? So a they suit the need for growing renewables, right? If you have the um yeah, if you have the necessary means of not directly, but using a smaller DC to DC converter which does not have a conversion stage, right, from DC to AC, they can directly be employed over there, right? So they suit the purpose of growing these renewables, right? So enhancing the renewables at this distribution side, right? Next, the advancements in energy storage systems. Given our batteries, they can store DC and they can give out DC, right? So uh yeah, because this is happening, the ESS, the batteries are becoming cheaper, and we can integrate them across the distribution side, right, to be able to support the need when the grid is in need of it, when there's a peak mode happening. So for that, this suits our purpose, right? Because you can directly connect it across a DC bus, right? And there are simple control strategy, right? Because your conversion stages are less, you are able to provide control over them very simply, right? You can just design a simple converter control topology to be able to. You don't have to have a power conversion stage, like for example, moving from DC to AC, right? And that is not something that is very convenient for developers. Next is direct connection to loads. You see, most of the loads that we use at our home are now becoming DC, right? You have your computers, right? You have your phones, your tablets, your lamps, even some there are uh, these LEDs which can work directly on DC. And you have, I mean, lighting loads or the lighting loads, right? So you have plenty of resources that can be directly connected across these. So this makes sense using directly a DC microgrid for that purposes, right? Now there is one big thing that this bidirectional converter, right? This bidirectional converter or all of these converters that we are using, we need to be able to provide control in such a way that we make sure that the bus voltage, right? What do you want from our DC microgrid? It's that the bus voltage, excuse me, sorry. Yeah, the bus voltage that we have, it stays closer to the reference voltage, right? And that is what we want from our DC microgrid. And that is what this control scheme essentially does, right? It takes a reference bus voltage, so it's a reference voltage, right? It measures continuously the bus voltage and it produces an error signal, right? This is an error signal. This error signal is then uh, fed to this PI controller. And why we are doing that? What this control scheme essentially does is it controls the converters. It controls the converters in such a way, the DRs, the batteries, anything that is connected, the grid, even exchange of power from the grid in such a way that the bus voltage that all of these devices are connected to stays closer to the reference voltage, right? And for that purpose, what they do is this control scheme essentially does is it modifies this power flow control strategy in such a way that What we want out from the system follows closely, follows the bus voltage closely as possible. And that is what is happening over here, right? So this error signal is sent to this PI controller, and what this PI controller is, it develops a command signal. So what is this command signal? It is a current, right? So when we talk about a DC microgrid, what are the control variables for a DC microgrid? It's voltage and power, right? Compared to our AC grids, we have power, we have voltage magnitude, we have voltage phase angle, and then we have frequency or Q. So we have a lot of control variables. But for a DC microgrid, the funda is very simple. It's simply, sorry, it's simply P in voltage magnitude. I don't even have to write voltage magnitude because voltage is just magnitude for DC bus, right? Yeah. So what this the difference of this error signal produces a current command signal. And what is the use of this current command signal? It is to figure out how much current needs to be increased from individual devices to be able to make sure, or increased or decreased in any way. I mean, the error signal can be positive or negative in such a way that the the bus voltage follows closely to the reference voltage. And how this PI controller achieves this is because it has this. If I want to write the signal, it will be like something like this, right? So what we have is we have a proportional constant which is directly proportional to the error signal, and we have an integral constant in which we are making sure that the error signal is moving from the zero to from some state to zero, right? And that is what this ensures. What PI controller wants to do is to achieve a zero steady state error, and PI controllers are quite efficient in that. They are able to effectively eliminate any steady state error, and that is what we want. We want zero steady state error, right? If error is zero, that means the bus voltage is closely matching the reference voltage, and that is what we want. And that is why PI controllers are used. This PI controller is then fed to this low pass filter. So why? Because this command signal can have some noise, some high frequency noise, and you want to reduce that, right? You want to reduce the high frequency noise before it is sent as a signal to the storage devices, or any of your controllers that are connected, even converters, right? Converters of these individual things, right? This is converter. At the end of the day, you are not directly controlling the battery. You are controlling the converter that is connected to the battery, right? And LPF ensures that the high frequency noise is attenuated, and that is what we want, right? Next, this command signal moves from this high frequency attenuated command signal moves to a rate limiter. And what this rate limiter does is it ensures that the output of the command signal or the low pass filter is a command signal only, does not abruptly change. Because if it abruptly changes, the battery or it could stress the battery or the converter, and rate limiter ensures that. So if I want to write this attenuates high frequency component, and this ensures that output command signal doesn't change abruptly, right? In a sense, what you want to ensure is it's free of any transients. And if you don't do that, if there's no rate limiter connected, and if this signal is sent directly to the converter that is connected across your battery, it could stress that converter, and that is not something that you want, right? Now what we have is we have another we send this low pass filtered current component command signal to your power flow control strategy. Now this power flow control strategy is a block, right? We will discuss what this power flow control strategy is over here, but just assume for a moment that it is a black box. And what this black box does is it takes in the account your how your batteries, your PVs, your SOC of the battery, how your PV is currently, how your grid is, etc., etc. How are they behaving at this point of time when you receive this command signal, right? And using them, it generates a reference voltage or a reference command signal or a voltage signal for each of these converters, individual converters. So what you want to do is, by controlling the power from the individual converters or the components of your DC microgrid, you want to ensure that controlling the power that is being outputted from these individual devices, how that relates to your voltage. Because at the end of the day, for a DC microgrid, P is directly proportional to V. Right? This we have talked about in depth in when we were discussing about DC microgrids. It happens because there's just current, right? And it's just not P. It's basically current, and the current corresponds to the active power component only, and there is only active power in DC microgrid, right? Now this power flow control strategy produces the reference voltage set point for your PVs, and for your batteries, and for your grid, right? For your grid converter, this grid side converter, to be able to set individually how these converters are behaving. And then each of these converters are, before passing these reference signals to these converters, we use a second stage of the control, right? Since from here you can see, right, earlier we had a bus reference voltage and we were measuring the actual bus voltage, right? And based on that, we were controlling how the individual store devices need to behave so that the bus voltage matches closely the reference voltage. And now when we are giving the reference signals, we need to ensure that how the individual devices are behaving to match the reference voltages or current signals that are being generated. And how does they do it? It's by changing the duty cycle, and that is what we are going to talk about right now. So these are the inner control loops. So this is the second stage of the control scheme that we have. The outer scheme was managing the bus voltage to be closer to the reference voltage. Now the inner control scheme, managing the received reference signal from the power flow control strategy, how the individual components need to behave. Let's talk about, and what do they do before being connected to the converter. What they need to do is they need to ensure that how the switching is happening for that converters. How do you impart control over converters? You impart control by changing how the switching is happening, right? Converters are what? They are made of switches, and by controlling the switch signals or gating signals, you are able to provide control over that converter. Similarly, for the battery, again there's an error signal. Again there's a controller. It could be PI controller or anything. Mm, then it is set to this limiter. Limiter ensures the same thing, that the output should not change abruptly. And then what we have is we have a duty signal which is being measured with a triangular waveform. This triangular waveform is used to ensure how is used to develop PWM signals, right? So what you have at the end of the day are pulse width modulated signals to each of your switches, and that is what is happening for each of them. Again, this ultra capacitor, you have a reference signal that is received from the power flow control strategy, and you develop switching how these gating pulses need to behave, right? That is what you want at the end of the day. Next you have grid. So grid is connected to a phase lock loop, and we have talked about what this phase lock loop is. It is used to ensure that the reference, or the reference that we have, the signal that we have received, it matches closely in how the voltage phases are, right? If it goes out of phase, if the reference that we are generating moves out of phase, then that means that our signal will no longer be valid, right? And that is what is happening. So what we are using, we have a unit sign template, right? So it's just a unit sign signal which has one minus, it's moving between +1 and -1, right? And what this does is it's just multiplying, it's just modulating this received reference signal onto this sine wave, and this sine wave behaves on how the phases are. So I'll just write in the grid. So you want to make sure that you don't move out of phase from how your grid is behaving, right? And then you pass it to a reference. Sorry, you you produce an error uh, signal, and this error signal is produced by checking what how the grid current is and what is the received grid current is, and then you send it through a hysteresis current controller. Not current controller, it's a hysteresis controller. So just like your PWM signal uses a duty signal, which is then imposed onto a triangular waveform. What this hysteresis controller does is it checks how much deviation is right now between different signals, and then it produces switching or gating pulses based on that. So you produce four gating pulses. Similarly, for your PV, you want to make sure that you are at your MPPT, if at all you want to operate at MPPT, and based on that, you check what is the PV reference voltage and PV actual PV voltage, and rest of the things are similar, right? And what you have right now is the switches that are present at the half bridge converter that is connected across to your PV, right? So these are the inner control loops which provide control over the individual converters. And based on that, based on everything that we have done right now, we are able to provide control over the bus voltage. And what we want to do exactly is we want to make sure that modulating how we are modulating uh, the signals to the converters in such a way that the bus voltage follows closely to the reference voltage, and that is what we want for any of the uh, this device that we have connected, and that is how inner loops are used. Right, and moving on. So this is a general control scheme. So control scheme to keep tracking the reference bus voltage. Now, as I mentioned, we used a power flow control strategy, right? This power flow control strategy. What it does is based on how much your individual devices are, whatever levels your individual devices are, it is used to um, get power out of them in such a way that you are able to provide control over your voltage of the bus. And that is what we want, right? From the beginning that I've told you that there are only two control variables in DC microgrid. It is the P and voltage magnitude, and both of them are dependent and correlated to each other. And this is how power flow control strategy works. Now, I have extensively discussed the PFCS last class. I won't be discussing this extensively. I hope that you have watched my previous lecture. If not, please go ahead and watch them. But I'll still talk briefly about these systems, right? Hmm. So, so this is a PFCS power flow control strategy for an energy management scheme. So I'll just keep it here. I guess let it be. Hmm. So let's talk about this. Hmm. So it's a simple flow chart, right? What you want to do is based on how much level your battery is, based on if you are at a grid connected mode or not, if you are having a peak mode or if you are not having a peak mode, how the devices behave in each of these modes, right? And there are only two modes that we have talked about, right? And the instructor has also talked about it. These two modes are three modes are sorry, there are two modes only. It's grid connected mode, and in this grid connected mode there are two more modes: off peak mode and peak mode. and then you have isolated mode. Hmm. Right. So when I say peak mode, what I usually mean is that if, let's say, the grid is experiencing peak power. When I say peak power, is that the resources that the grid has uh, are at the end, are at the extreme of their production level, right? So that means that the grid is experiencing huge uh, um, load, right? It's experiencing huge load, and it is not able to provide any extra load that you want from the grid. And that is where all of this things come. So let's talk about these individually, right? So the first thing that you check is when you start, the first thing you check is whether the grid is available or not. If the grid is available, and you check then if it is a peak hour mode or not. If it's not a peak hour mode, you move to C. And what is C? This. When it's not a peak hour mode, what does that mean? That the grid has available power. Now, if the grid has power, will you be exchanging it directly without checking how much your resources are? No, right? So what you do is you check if the generation you have is greater than load. Let's say the generation is greater than load. If the generation is greater than load from PV, then you check if the battery is at a higher point of the SOC. So the batteries, the maximum SOC is set at 90%, right? So you check if it is greater than 90%. If yes, what you do, you don't take power from the grid. You keep grid as absent. Your battery is either charging, it's either discharging or idle, right? You can discharge if you want, but you can keep it at idle. Your PV operates at MPP, and your load, what you want to do is your load you want to sorry yeah your load, what you want to do is your load, you keep it as full load. So all the load, so I forgot mentioning, but the loads are divided into two categories. It's either essential load or critical load, or non-critical or non-essential load, right? So you don't keep grid as absent. I'm sorry, I misspoke. You absorb. The grid absorbs extra power because you have extra generation. You just transport that available power to the grid. So grid absorbs that. But it's not going to be the same case indefinitely. There can be at times when you don't want grid to absorb that much amount of power. So what you do is you ensure that your PV is operated at such power level that it is only meeting the load. Because it may not so happen that the grid is absorbing power at all times, right? If it does not have any, so I don't know if you have heard, but there are instances in the markets, power markets, that there are negative LMPs. What do negative prices mean? So negative prices means that the grid operator is willing to give you money to increase your load. That's precisely what negative prices mean. That if you are generating, the grid operator wants money from you, if at all you are generating, right? So that is what negative prices are essentially, and it may not so happen that the grid operator would always want you to keep absorbing extra power that you are generating, right? But let's say, yeah, so let's say that your SOC is not at 90 degree. It's not at 90 degree. So what you do? You keep your grid as idle or disconnected because you don't want to the grid to absorb any extra power, right? Your battery absorbs the extra power. It charges, that means it charges, and your PV operates at MPP and your load is full. Right. And based on all of this, I mean, I won't go into details for all of these modes, but it makes sense, right? If you go through it on your own, this is what this whole power flow control strategy means, and it is highly intuitive. You don't even have to check with a great deal of interest, right? It's fairly very simple. It's intuitive. We know if there is extra amount of power, what will grid do? Will it stay idle? If you have battery, will it charge or not? It's fairly very simple, and I don't want to go through all of that. That doesn't make sense either. right? So that is what we want, right, from this power flow control strategy. How to provide control, if at all there is this control in the system. Sorry, how to control so that we are able to meet some targets that we want. And what are these targets? Why PFCS? If I just say, what you want is, you want peak demand reduction, right? You want to reduce the peak demand that is happening, right? If the grid is experiencing peak demand, you are able to supply that power, because the DC microgrid could at times be generating excess, and that is what it will do when grid is experiencing peak power, and that is what usually happens. So when there is peak power, you see, you check if generation is greater than load. If it so happens, right, and if SOC is also at a very high level, 70 degree, your grid absorbs that extra power, right? And your battery is at idle or disconnected. And you see, your SOC level now you're maintaining is only 70 degree. You just want to check. Why is it happening is because even though battery can be at 70 degree, you will have certain buffer. You have that 70% buffer, but you don't want to ensure that it's at 90 degree. Why will you have it at 90 degree and charge all the way, right? So the amount of maximum charge battery can hold depends on the mode that you are operating, right? For example, if this A case that I talk about, right, this A case comes from this. If the grid is not available and if the power is not generating enough, right? If the PV is not generating enough power to meet all the load, you check if your battery is at 30 degree or 30% or not. So the load limit, you further check if it is at 30% or not. If let's say it is at 30%, you further check if it can go down. So the maximum power at maximum SOC that battery can have, or the minimum SOC it can have, depends on the mode that you're operating, right? And that is what it should be, because it's a flexible load. So based on all of that, what we want to do is we want to check how the operation between different modes is happening, right? And what we want is we want smooth transition between different modes of operation. So a PFCS ensures smooth transition between different modes. Let's say if I keep, if I just say that maximum battery SOC can be 90 degree and minimum can be 10%, right? So even when the battery is at 70% and the grid is not available, it will try to charge itself to reach that 90 degree cap. But that is not what we want. We want it to discharge even if it has 80%. So that is why we keep that limit dynamic based on how, and that is essentially what PFCS is, right? This ensures that the limit is kept as dynamic as possible. Right. And next is this PFCS. Based on this, we can have effective and efficient control. Effective and efficient control. Next, we have based on how much the battery is holding, we can reduce the stress it incurs. Right? It reduces stress on battery. Last, what we want to do is we want to increase life of storage system. By keeping that maximum minimum limit dynamic, we are inherently enabling the by we are inherently making sure that we are increasing the lifespan of these storage devices. Right, and these are what the level of different modes are. And let's talk about these modes in some way, shape, or form, right? Let's discuss this here. What does being off peak means? Off peak means that the conventional grid can deliver power because it is not experiencing any peak. And what we can do is we can ensure that batteries can be charged, right? And at the peak mode, grid needs power, right? And last node is isolated mode. Why am I writing all of this is because next I'll just talk about a few waveforms that we discussed in the class, and over there these things come, and I want to ensure that all of us are on same page, right? And isolated mode, that means the grid is no longer available, and if grid is no longer available, that means you cannot you have to check if you have sufficient generation available or not, right? So you check if PPV is less than PL. So if your generation is less than load and your SOC battery is also less, I won't set a limit, I'll just say it is less, or I'll say is critically low. Is low, I'll just write is low. So if that happens, what does that mean? So yeah, right. Hmm. So what does that mean? So you, let's say that you don't have sufficient generation available and you have no grid connected to yourself and battery is also low. That means you have to shed some load. So load shedding is inevitable, right? But if opposite happens, PPV is greater than PL and SOCB is very high, then you have to operate PV at off MPPT. So you have to derate it. Nice. Next, what the instructor did was it showed how the simulations were conducted. So, what kind of simulations did the instructor conduct were based on this PFCS, based on this DC microgrid. It had interconnected DC microgrid, various different case studies, right? It simulated this based on different modes that it was connected to. Then, if let's say it did a case study where two isolated DC microgrids were interconnected, and then he did a study where the control coordinated voltage control scheme that we discussed previously, right? All of these videos were shown. Um, see, I'm not going to talk about these videos, right? Because that is not something that I have experience with because the hardware was available over there, right? So that is not something that I can do. But yeah, don't say that I'm not. But uh, you have to watch that video and frankly, sorry, frankly, these lectures are supposed to just be aiding you, right? These are not supposed to um be completely switched with the instructors lectures that are uploaded on the NPTEL portal, right? And so make sure that you go through them and then come to this lecture. It'll make your life easier. It'll make my life easier as well. Yeah. So for this, all of this the hardware that the instructor needed. It needed the RTDS for real-time simulation. I've talked about the simulation a lot of times in the last class. We discussed PPT as well, a very beautifully made PPT that explained what real-time simulations are, what control hardware in loop simulation is, what PA power hardware in loop simulation is. I won't go into details. So this is the main hero behind all of that, right? The main protagonist that is used to simulate all of these different devices that you have. This right here, what this is a power amplifier. What this power amplifier does is, I'll just write, this is a power amplifier, and this is RTDS racks for real time simulation. Hmm. So what this power amplifier does is it simulates the environment of AC microgrid or a DC microgrid if you have. Right, and it supports by modeling it as a microgrid. Yeah, it generates waveforms. Next, you have uh, the solar panels, right? Silicon crystalline based solar panels. Then you have PV emulator. So if you don't have the solar PV panels to generate real time values, you can use a PV emulator as well. It's a chroma based PV emulator. You use DFIG to emulate wind energy systems, and you have diesel generators as well. And the instructor also had a hybrid battery energy storage system where it used uh, uh, it's lead acid or lithium. It's a lead acid battery in conjunction with ultra capacitors, right? So this is what the instructors hardware was, and then they did CHIL, PHIL validation. I won't go into their details. And they simulated four different case studies. First two case studies were control hardware in loop validation, where they talked about power flow control strategies that we just discussed, and the isolated DC microgrid operation. And in PHIL, what they did was they integrated DCMG, the DC microgrid, to IIT Roorkee's network. We'll discuss this next. And the last they did was coordinated voltage control for IEEE 33 bus system. So this coordinated voltage control scheme we have already discussed in the last lecture. So please feel free to rewatch that lecture if you haven't. So the first case study they discussed was PFCS, right? How the power flow control strategy is being implemented. And they did it via CHIL validation. So what they simulated was they simulated the three modes, peak mode, off peak mode, and isolated mode. All of these modes, what they did was they modeled the battery status as either absorbing, idle, supplying, right? And they take grid status as either idle, supplying, or absorbing. And you can see that the grid was not present in isolated mode, and because an isolated mode does not have a grid connected to it, right? And when the grid was connected, they modeled PCAR modes for PCAR when PCAR was happening, and non-PCAR modes as well, right? So yeah, and these are the different time intervals that we will show in these waveforms. Now, as you can see, so these are the different operating conditions of the DC microgrid and the status of battery, right? So the first case is case 2. Now, please take a look. I mean, please be, you know, a little present over here. So in the first time step from 0 to T1, right? What you have, your battery was absorbing, right? Just a second, I don't know why. Yeah, now it's, hmm, just do it like this. Right, so your battery was absorbing. So when your battery is absorbing, what happens is, that means this. If you see from 0 to T1, this is 0 to T1, and you see your PV is supplying power, right? It is supplying power. That is why it is, sorry, yeah, here. That is why this is positive, right? And because your PV is supplying power to the system and your battery is absorbing. So since battery is absorbing, it is modeled as negatives, right? So you see, this is the zero line, and below that it means that the waveform is negative, and when it is negative, that means the battery is supplying power. The current is negative in that. And you see the ultra capacitor is used to power only the transients, right? So you see here switching between battery happened, right? And you see the battery supplied transient here as well. there was switching battery. So transients, whatever transients are present in the system, the main goal of the ultra capacitor is to supply them, if at all there are any, right? Then you have the load. This is modeled over here. This is your grid side voltage, and this is your grid side current. How much current you are exchanging, right? So we'll discuss. So the first case is this one from 0 to T1. That is, the battery is less than 70%. That is why it's absorbing, and the grid is idle. So you see, grid is idle. That means it's not supplying any power. So up till T1, that is still here, the grid is not supplying any power, and the battery is absorbing, and the PV is generating as it should be. And you see, the main goal of our PFCS is to keep bus voltage at reference value, and that is what is happening. The bus voltage is at its reference value. Right, the next case that happens is case 1. Now the battery is at greater than 70% and you have excess generation. The load is less. So you see 2.5 kilowatt and load is less. And this is the case 1 from T1 to T2. Your battery now moves to idle. Your battery won't charge because it is at greater than 70% level. And now your grid will absorb power because you have excess generation available and there is a peak mode. When there is a peak mode, the grid won't supply you power to charge your battery if you have excess generation available. But if you have a fully charged battery, you can supply that excess generation you have available, right? So the PV continues generating what it was. The battery moves to zeroth level. This C3 where this is connected, right? You see, it shows this thing. This is grounded. That means that the voltage is at zero. So this is the reference value, right? So battery moves to zero. The transients are still being supplied by the ultra capacitor. The load is still at the same value that it was, but now what you see is there is some current being exchanged with the grid. Now, how will you see what is happening with the current? You can see it over here in the magnified version of this graph. So you see, the current exchanged was zero. As soon as the PFCS mode changed, the battery is now charged to 70%. Your grid now starts absorbing power. And how do you see that? You see the current is out of phase with the voltage. So when the current is out of phase with the voltage, that means it is importing power from the microgrid, and that is what is happening in this mode. Moving on, then comes case 3 from T2 to T3. What we have is your battery status is greater than 30%. So now your battery is at 70%. There is a peak hour. You can't import power from the grid. And what you have is your PV is less than PL. So you are not generating enough. And you check if your battery's SOC is greater than 30%. If it is, if at all it is, you see PV is now at a lower level because it's not generating enough. So your battery kicks in. The current from your battery becomes positive. So that is it. It means it is delivering power. And you can see the voltage is still constant, and you see any transient that the switching operation produced was supplied by your ultra capacitor. The load was met, and you were not importing any power from the grid because the grid is experiencing peak. Now, let's say that the battery is less than 30%. So you will continue supplying even if it is less than 30%, it still supplies and your grid is still idle because you don't want to exchange power from the grid because it is experiencing peak power mode, right? So you move to this. So your generation is less than load. Your battery SOC is also less, right? And but you continue discharging your battery because it is not critically low. It is less, but it is not critically low. So you see over here, the voltage is still being managed. Your so it should be T3 to T4, right? Yeah, it's T3 to T4. So we'll talk about this. Your voltage is still at the reference value. The power coming from the PVs is less. So you will continue. Oh, sorry. There's a load shedding happening. So let's see. let me see over here. If there is a peak mode, okay, so grid is available, but there is a peak hour. So you check, you see if the battery SOC is less than 30%, you move to F. F is you check if it is less than 20%. If it is not, grid is still idle, battery still supplies, PV is MPP, and yeah, there is some load shedding, right? So you had three loads. Full load is what? Full load includes, hmm, full load includes 2 NEL plus 1 NEL. Sorry, 1 EL. Right, but now since your battery is not at that much level, you want to conserve as much energy as possible. So you shed some load. And while shedding this load, what you do is you you can see over here, the battery is not giving it out more energy because it is at less than 30%, still greater than 20%, but less than 30%, and the load is shedded. Now your load is less than what it was before, right? So that is what happens over here. Then it is less than 20%. But let's say from T5 to T end, when it becomes extremely critically low, that is less than 10%. So you see T5 to T end, your battery becomes, so I did not discuss T4 to T5, sorry. So let's discuss T4 to T5. Your battery has now, it was earlier between 30 to 20, now it is between 20 and 10, right? Now if it is between 20 and 10, you continue discharging, but you shed more load. Earlier you had one essential load and two non-essential, one essential load and one non-essential load. You remove the non-essential load, you completely cater to the essential load. So you see over here, yeah, over here, sorry. So you were generating some, but it was less. It is still greater than zero. It was less, but you were generating some energy and you shed more load. So the load is less now. So you see, the load is, it becomes more or less. But now from T5 to T end, the battery has now reached less than 10%. So now you have to import power only for the critical load you have. So PV is producing less. Your battery now switches off. It's disconnected because it cannot discharge more. And now you import power from the grid. And as you can see, how to check if you're importing power, it is in phase with the grid. The current that is being exchanged with the microgrid is in phase with the voltage of the grid. So this is how power flow control strategies work, right? Based on the modes that you are operating, based on how your energy levels are, based on whatever you are doing, you want to switch between all of these loads, and that is this thing. The next thing that they discussed was a PHIL experimentation setup where they integrated a DC microgrid to IIT Roorkee's network, right? And how did they do it? They did it through this model. They used RTDS, but what they did was they controlled all of the power hardware, that is converters and anything that you have, right? And and how did they model the system was because they had to ensure that the DC microgrid is being integrated to the IIT Roorkee's network, right? So what they did was they reduced the Indian power system. So our original Indian power system network is this. It is a huge network system, right? So when I talk about huges, it's there are a few things, right? If we talk about today's scenario, the peak demand that the grid experiences is around 250 gigawatts. The peak, so the total generation capacity that we have is around 450 gigawatts, out of which renewables are, how much are they? I guess they are 190 gigawatts. Someone can check around 200 gigawatts, I'll write. You just check this number once, right? But the complete Indian power system network is huge. It has huge transmission network. And this transmission network, I mean, the instructor had data from 2013, but in 2025, I mean, give and take a few years, this network has reached 4.8 lakh circuit kilometers. So you see, if you take all of these wires and then you just keep them extended across the whole network, they will extend to a 4.85 lakh kilometers length, right? So this power system network is huge. Now what you want to do is, you want to retain the dynamics of the system, right? But to simulate it, you want to ensure that the reduced system that you are taking, so you don't take this huge network. We'll discuss. So let's discuss. So the power system network is huge, right? You see, it is a huge system with many lines, buses, right? And what you do is you reduce this Indian network. And this reduction is done because you want to study the system. But the system in itself is very complex. So you want to reduce the order of that network. And this order of the network it reduced and they took was 120 buses and 216 lines. When I say zones, it just simply means that there are 120 buses. So you see individually the buses are over here. Right. And what we want to do is, how do we want to do is, let me just talk about why. So why reduced order system? So power system networks in real world is very complex. They are very complex. So when I say they have huge number of buses, huge number of interconnection branches, lines and stuff, right? So what you want to do is to study the system. You want to reduce the order of it, right? And so by reducing the order, what you do is you yeah, you find computationally tractable system. So if you want to use mathematical models, right, for analysis, you want to make sure that the analysis that you want to do is computationally tractable, right? A model can be solved in infinite number of time steps, and it can be solved in smaller time steps as well, right? So what you want to do is you want to reduce the order of the system. So instead of having 26,000 buses, you can have 120 buses, right? That is what I mean. Instead of having a huge number of lines, you can have lesser number of lines. So let's say, for example, if I take 2013 data that the sir had, they had around 6,034 buses, right? And 6,034 buses are huge. So what do you do is you reduce the order to 120 buses. And that makes sense. It will give you a computational tractable solutions, right? Why? Because for each bus, you want to find out magnitude and the reference voltage angle, right? Sorry, voltage angle for each bus. So that means you have 2 raised to power n variables to find out. 2 raised to power 6034. Sorry, that's uh, no. I shouldn't say 2 raised to power this is second. So if I have 3 buses, what I have is 2, 3, 4, 5, 6. Mm. So it's 2 raised to power n minus 1, I feel. What we have is this is known 1, 2, 4. 2 raised to power 3, 8. Yeah, 2 raised to power. Oh, sorry. I'm saying 2 raised to power. I should say 2 multiplied by number of buses. My bad. So you have 2n. Why was I saying 2 raised to power? I don't know. So you have 2n, right? So for each bus, you want to find out. For each bus, you find out voltage magnitude and angle, right? We generally have a reference bus and we know it is at 1 angle 0. So in essence, you want to find out for 2 n minus 1 buses. So these are the number of variables you need to find out. For 6034, this is a huge number, but for 120, it is not a very huge number, right? That is what I am saying. So by reducing the order, you manage to find out a computationally tractable solution, right? So how do you do it? You reduce the order of the system. So reducing the order by preserving the inherent dynamics of the system to be modeled. So you want to reduce the order, but you want to ensure that the essential dynamics of the system that are there, we are able to model that, right? So I won't go into detail how this happens. So what I'll just give you a brief overview, right? So let's say you know that there is this zone, right, where there are multiple buses connected, right? And there is this zone where there are multiple buses connected, this zone, and this zone. So what these essentially are, these are your RLDCs, your northern uh, load dispatch center, your western load dispatch center, sorry, your northern load dispatch center, your western load dispatch center, your southern load dispatch center, your eastern, your northeastern, right? So you have all of these load dispatch center, you can keep them as bus. And what you'll have is you will have a 5 bus system, but you won't be able to maintain the inherent dynamics of the system because you have reduced too much. From 6034 buses, you have come down to 5 buses, right? So that is not something you want to do. So how do you do it? I won't go into detail. There are mathematical models that are being developed which are used to, uh, check how the dynamics behave by keeping the buses at some whatever level there that you want to keep. But there is a very interesting paper developed by my written by my supervisor, where for an ERCOT managed system, right? So ERCOT is the independent, like for example, NLDC or POSOCO or Grid India is our system operator. ERCOT is the system operator for of Texas. Texas is a state in US, right? So what she did was she modeled their system, and she created a reduced order system, two reduced order system, one a 200 bus system and the other 8 bus system, right? By keeping the dynamics as close as possible, you can go and check out this paper if you have an interest, and if you want to pursue this research direction. I won't go into detail, but what I wanted to discuss was how this reduction on this happens, right? And by reducing this system, they picked out the buses of the Uttarakhand state. So this is what they did. They took out Uttarakhand as a test system, and they modeled all of that over there, right? And they did a PHIL experimentation of integrating a DC microgrid to Uttarakhand's network, right? And this is what they have written over here. So this is how things happen in if you want to simulate for a real world scenario. Moving on, next thing the instructor discussed was system analysis of an AC-DC microgrid or an AC-DC distribution system. So what I mean by system analysis is that distribution system. What are distribution systems? So if I talk about distribution systems, these are radial predominantly. I'll just write, but they are available in meshed or loop topology, right? The other thing that they have is they have a high R by X ratio. When I say high R by X ratio, it means that the resistance dominates uh, the reactances, right? And now, due to this high R by X ratio, the conventional power flow control schemes, sorry, control schemes, I'm saying the power flow studies, right? The Gauss-Seidel, the Newton-Raphson. So, what are the power flow studies? Gauss-Seidel, Newton-Raphson, or fast decoupled load flow. These are no longer applicable to this. Why is that? Because these studies are predominantly made for transmission systems, which assume uh, that the system has inherently reactances in it, right? So the R by X they consider is very low. Assumptions assume. So these are for I'll just write transmission system. Assume R by X is low. So if R by X is low, what does that mean? That means that these studies are able to perform well. And why does that happen? So I don't know if all of you are able are sorry have studied these different power flow studies. So I won't go into details because that is not something. I'll just assume because it's a prerequisite for the course. I'll assume that you know what power flow studies are, right? So what is essentially the Newton-Raphson or these do is they generate a Jacobian matrix. So what is a Jacobian matrix? So Jacobian matrix is a square matrix that relates the sensitivity of P and Q to mod of V and delta, right? So what they do is they relate how P and Q are sensitive to the mod of V magnitude or the delta, right? And how, if you want to write, they are something like this. So because this low R by X ratio is generally assumed, so you will generally see that these terms are dominant. So when these terms are dominant, because P has a close relation with delta and Q has a close relation with mod of V, and because these are sensitivities, these Jacobian matrices that are developed, they are highly sensitive. Highly diagonally. Sorry, they are diagonally dependent, right? So they have high, what should I say? They are diagonal matrices. Assume that they are diagonal matrices, right? Now, but what happens when, if I want to talk about it, their update rule is written something like this. So J del X is equal to minus f of x, right? And this translates to xk plus 1 is equals to xk minus j inverse f of x. Right, so what you want to do is you want to update these values based on the Jacobian matrix that you develop for each iteration, right? Now what happens is that the Jacobian is diagonally dominant for transmission system. It happens. But at the distribution side, that is not the case because of high R by X ratio. And that means for distribution systems, the Jacobian becomes ill conditioned, right? What do I mean when I say that they become ill conditioned is because they are susceptible to small changes in the input value. Great. So that is what happens because these are the Jacobian becomes ill-conditioned. And why does that happen? Because of high R by X ratio. Because the R by X ratio is high, that means the Jacobian is no longer, so this does not, or I should not true for distribution systems, and this is also not true for distribution system. So that means the Jacobian is no more diagonally dominant, right? And therefore it becomes ill conditioned. And if they are not diagonally dominant, that means that, and to check ill conditioned matrices, there's a very easy to check that if I want to see, this refers to the fact that rows and columns become nearly linearly dependent. So if I say, for example, A would look something like this: 1.0.999, 0.999, 0.998. So you see all the values are closer to 1. So that means that the rows and columns are now linearly dependent. So this and this are very close to each other. The row 1 and row 2 are very close to each other, and column 1 and column 2 are very close to each other. Because they become ill conditioned, so there is this that there is this thing that happens is that the solution becomes difficult to ascertain, right? And why is that? Because now you have redundancy in the system. So I don't know if you are familiar with linear algebra. I'll assume that you are familiar with linear algebra. In linear algebra there is a term called as rank of a matrix, right? And rank of a matrix says that i- if a rank of A, and let's say there is X, right? X1 and X2, I'll just assume rank of A, if it is less than rank of X, so what you have is you don't have unique solution. There is redundancy in the system. There is a redundancy because you have linearly dependent rows. So if you check, these are very close to each other, so the rank will be only 1, right? Since this matrix, the other matrix that you have of x1 and x2, the rank is 2, right? So 1 is less than 2, you don't have a unique solution, so your solution won't be there. And how do you check this? So if you want to check if a matrix is ill conditioned, let's take an example. So let's say I'm taking the same A, 1, 0.999, 0.999, and 0.998. I want to get x1 and x2, and I have B. Let's keep the value of B as 2 and 1.99, right? So how you do it? You do it, so this is A, this is X, this is B. So X would be what? A inverse B. So let's check. So I'll just, I don't know if you will be able to see it. I'll just do it, right? I mean, so if people know this, I'll just share my screen, Chrome tab, window, right? So let's check if I'll go to the matrix calculator and I'll just write these values, right? 1, 0.999, just decrease, and 0.999 and 0.998. I'll inverse this and I'll insert in A, B, I kept only 2 and 1.999, right? If I find the answer, X would be what? 1001 and minus 1000, right? You see the answer was this. So coming back to my screen, I'll just stop representing. Wow. So just a second. So it's visible, right? So you see x is now how much? 1001 and minus 1000, right? And similarly, I'll just do full screen. Yeah. And now what you do is you just increase b, instead of keeping it like this, just increase the lower term by 0, 2 point, keep it 2.001. If you keep it 2.001, find the x. So I'll just not do it like I won't change screens. I have to shift screens multiple times. So I'll just solve it and I'll give you the final result. So if I do it 2.001, if I solve, the answer comes out to be 299 and minus 3000. So you see, when I said the matrix is ill conditioned, right? I just said the matrix will be ill conditioned. And since the matrix is ill conditioned for the distribution system, this Jacobian becomes ill conditioned. What happens is small change in the input values produces a very large change in the output value. As you can see, the input value by changed was only 0.002. I just changed B2 by 0.002, right? I just increase it by 0.002. But the x variables that I found out were very huge. The difference was very huge. So you see, instead of the if instead of being closer to minus 1001 and minus 1000, it is now 2999 and minus 3000. So you see, this is what Jacobian does if it is very ill conditioned. And because this happens, the in each iteration, the step will have so noisy uh, gradient, so noisy changes that the solution will, you will never be able to find the right solution for that. And that is precisely what happens over here, right? So what you want to do is, now we have proven, right? We have proven that the Jacob, because the inherent load flow studies, they use Jacobian, and these are no longer applicable to your distribution system. So what do we now use? Should we now just simply be not using anything? No. What you use is, you use forward backward sweep method. So let's discuss what is forward backward sweep method. So what is forward backward sweep method? Let's assume that you have a 3-bus system, right? I'll just assume I'll connect a 3-bus system. So this is a 3-bus system. This is bus 1, this is bus 2, and this is bus 3. And what you have is, you have S3 over here, you have S2 over here. You have some load connected to 2 and 3. This is I12, power flow between bus 1 and bus 2, and this is I23, current flowing between bus 2 and bus 3, right? And we assume that voltage at bus 1 is 1 angle 0, reference bus voltage, right? Now what you do is, you do first, so it's easy to calculate currents, individual current, right? If I want to calculate I3 and I2, what do I need to do? I3 is nothing but S3 by V3, and I2 is nothing but S3 by V2. Sorry, S2 by V2. So assume a flat voltage start. Start with flat voltage. That means keep V2 and V3 as 1 angle 0, right? You do that and find out I3 and I2. If you find out I3 and I2, what is I23 going to be? I23 is simply I3, and I12 is I2 plus I23, which is I2 plus I3. So this is nothing but, this whole thing is called sorry, not this. This whole thing is called backward sweep. So you first find out your currents in different lines, right? Once you find the currents, what you do is, you need to find out the voltages. So what you do, how do you find out the voltages? So you do a forward sweep. What is forward sweep? V2 is nothing but V1 minus I12 Z12, right? You know V1 is 1 angle 0. You know Z12, you know I12, right? You did a backward sweep. And V3 is what? V3 is V2 minus I23, Z23, right? So this is called as forward sweep. And you do it till the time V2k minus V2k minus 1 is equal to a very low value. Let's say 1e. So let's say 10 raised to power minus 3. Similarly, V3k minus 1 is 10 raised to power minus 3. So you do it till it converges, right? Once it converges, this forward backward sweep is so this thing works on what? This is simply KCL and KVL, right? And that is what we used. And that is how we do a forward backward sweep method for finding out power flow in distribution systems. So moving on. So we talked about how power flow strategies need to be changed for a distribution system and why does that happen, right? So you see, this is an AC-DC distribution network. What is an AC-DC distribution network? You have, if you see, you have your utility, you have your converters, you have your DC voltage generations available, right? This is DC, this is DC. And what you have is, you have demarcated all the buses, all the lines into either being AC, either being either being characterized by AC power flow or DC power flow, right? So the blue buses and the blue lines are DC power. They cater to DC power, and the orange lines and orange buses cater to AC power. And this is a schematic of an AC-DC distribution network. And as you can see, this is a meshed. Sorry, this whole thing is a meshed network. You have radiality plus you have loops. These loops are also present, right? So this is how a standard AC-DC network looks like. Now to find out, you have how many buses? You have AC buses and you have DC buses. And each AC buses are then characterized as one slack bus or reference bus. Then you have PQ bus, which is a load bus, and you have a PV bus, which is a voltage controlled bus, right? And in DC bus, you have either your P, sorry, DC load or P bus, or you have your V bus, right? So either you have a DC load bus where you have some DC power connected or where you are consuming some DC power, and you have V bus where you are just keeping voltage as constant, right? And that is what you do in DC microgrid. You want to keep your bus voltage as close as possible to the reference voltage, right? Now, if I say how these different buses are characterized, so you can see for a slack bus, you just keep it as reference, right? So you know V and delta, right? You just keep it as 1 angle 0. For this bus, you know P and Q, right? But V and delta are unknown. And for V bus, you have P and V known, while Q and delta are unknown. Similarly, since it's a DC bus, you just need know P, and for a V bus, you know mod of V. And that is what these different buses are in characterized here in this diagram, right? Now, we've discussed that conventional load flow suffers here because we have power modeling issues because there is a high R by X ratio. But the other thing that we need to do is we need to model how the DGs are consuming these power, right? So we need to model these individual distributed generations available, these wind farms, this, and this, right? And the converters, the voltage source converters, and this DC-DC converter, all of them need to be modeled properly. And if we have storage, if at all we require one, right? So these are some issues that we face. And what we do is we want to model these DC buses. And how do we do that? So these models are demarcated into different types. The type 1 caters to those that can only deliver active power. So if I have to give you an example of what can only deliver active power, it is, for example, your fuel cell, right? A fuel cell is only able to deliver active power. So an example can be fuel cell, or let's say your PV without reactive control. So if you don't have any reactive control, what you have is essentially just active power being taken from the DG, right? The second type of modeling is type 2 modeling, where what you do is you can deliver both active and reactive power. Right. So if I say you can deliver both active and reactive power, what are these resources? You can either have, so what can deliver? Okay, your diesel generators, right? Your BESS connected to a converter, your PV with active reactive power control, these can deliver. These are type 2 modeling of DGs. Next kind of modeling is type 3, where what you want to do, you want to deliver only reactive power. So these are your synchronous condensers. I don't know if you have heard. Your statcoms, right? All they need to do is they just need to maintain the voltage by changing the reactive power absorption or supply. The next kind of last kind of DG modeling is type 4, where you deliver active power but consume reactive power. And what is an answer for this? The answer is induction generators. So what do they do? Induction generators, they need to develop a rotating magnetic field, right? To develop that rotating magnetic field, they need to consume reactive power, right? But at the end of the day, what do they give is they give electric power, right? So induction generators are one such distributed generating device that deliver active power but consume reactive power, right? So based on these modeling of these DGs and based on the modeling of the converter, so you need to model the converter as well, right? So let's say the voltage source converter that is present over here, right? How do you model this? You model this by using this simple converter model, right? Where what you do is you check what is E2A by E1A, or you check what is I2A by I1A, right? So if you want to say what is E2A by E1A, it is either, so it's buck, right? So it's D or 1 upon 1 minus D for boost, or D upon 1 minus D for buck boost, right? I hope you all know, right? D is duty cycle or duty ratio. So this is for buck, this is for boost, this is for buck boost, right? So that is how you model your converters, and based on all of this you can easily model the power flow for the so you can model the power flow, sorry, load flow for your AC/DC distribution network, right? By using this forward backward sweep method, by using the model of the network, by using the model of DGs, and by using the model of your buck converter and boost converter. Right, so I discussed distributed generation modeling in detail before, so I had this page, but I don't know why I didn't use it. So this was discussed in your this week's lecture. So this is how a typical so the last class we simulated a simple DC microgrid, an isolated DC microgrid architecture, right? And for this DC microgrid architecture, what we had was we had a grid tied inverter. What is a grid tied inverter? Inverter which is between your grid and your DC bus, right? And based on that, there were separate control variables. And what were the control variables? At the zeroth level, you want to control the grid tied inverter variables. What are the grid tied inverter variables? So these are your voltage that is coming out of it, how the switches are being used, and etc. Right? The internal control variables of your DC grid tied inverter. And you see these are very fast in nature. So they are predominantly, uh, so their response time is very quick. Now, the primary control layer for this architecture is to provide grid support or automatic load sharing. So you should be able to share load between different loads, and you should be able to provide support to the grid if at all it needs. The other thing that you want is a secondary control, which requires microgrid synchronization or V and F control. And the tertiary control is optimization of the whole power network or the power flow control. And this is the slowest control of them all. So we've discussed all of these control layers inherently over the last period of last class, even today as well. I won't go into detail, but I'll just discuss this one thing. This is a very good visual representation of what kind of services the grid tied inverter provides. So you see the grid tied inverter based on the the mode that it is connected with. Let's say this G means grid tied, I by A means islanded or autonomous, GI means going from autonomous to grid, or I by A means going from grid to autonomous, right? So based on that connected, the kind of grid support that they can provide varies between stability. So for stability, what you want to do is you want to ensure active power regulation, you want to ensure reactive power regulation. They can also provide grid supports by using grid harmonic filtering, local harmonic compensation, and you want to ensure that you have VPCC feed forward and fast IG loop. So the current loop and point of common coupling control loop is very fast. The dynamics are fast. So what you have is low LVRT. LVRT is uh, s- I forgot LVRT. Low voltage. What the how can s- I don't know. My brain is not working. Just oh, right through. Yeah, sorry. So low voltage right through. What does this mean is that, for example, when your system is in extreme pressure, right? When your system is connected to, let's say, um uh, wind power generators or solar power generators, right? And there can be periods at which the voltage sags. And when the voltage sags, that means that there are periods of low voltages, right? And at these period of low voltages, how your grid tied inverter is able to maintain the kind of operations that it was providing when the grid voltage was not very low, right? And that is why it's written over here resiliency to voltage sags. When the voltage sags to a critically low level, how your grid tied inverter is able to ride through that whole scenario, right? So all of these functions, whether grid tied, autonomous, or between or transitioning from grid to autonomous or autonomous to grid, how it is able to provide a stability, grid support, scalability, and flexibility. This sums up the whole thing, right? So this we have covered extensively in previous classes, so I won't go into detail, but if you have any doubts, you can just uh, send me a message and I'll be happy to uh, talk to you, right? So this is all that was discussed in this week. So it was predominantly demonstrations only. So what we discussed was energy management schemes, the power flow control strategy, and how between modes of operations this power flow control strategy switches. Then we discussed one case study. We moved to how reduced power networks are developed, why are they even needed, and what for AC/DC distribution system, how do we, what kind of challenges we face for modeling the load flow, why the load flow studies that were available for transmission side not be inherently be used in distribution side, right? All of the Jacobian, everything we discussed in this week. We also discussed a load flow method which is forward backward sweep based on KCL KVL. Then we discussed types of distributed generation modeling, converter models, and then we moved towards a typical architecture of a DC microgrid, and the instructor ended with the demonstration of DC microgrid, right? So I'll stop over here and we'll move to question and answers. So sample problem session. Let's discuss questions. I don't know if some people don't join, so I have to do it on my own. Anyways, I don't have any trouble doing it, but it will be nice to see people answering questions once in a while. Right. So the first question is a bidirectional DC-DC converter can connect PV panels to a conventional three-phase grid. Okay. So you have PV panels which are DC and you have conventional grid which is AC. So what kind of conversion stage do you want to use? You want to convert DC to AC. So can DC-DC converter be used? No. So this statement is false. Next, ultra capacitors are connected to DC microgrid using AC-DC bidirectional converter. Okay, let's see. So you have ultra capacitors, these are DC, and you have DC microgrid, which is DC. So what do you need? You need a DC-DC conversion stage, right? So this is also incorrect. So the first answer is both are false, D, right? Next, the AC-DC distribution system is more complex than a pure AC distribution system. Correct. So in AC-DC distribution system, you have you have different DGs, right? You have too many conversion stages. You have voltage source converters. You have grid tied inverters, stuff, and a lot of stuff, right? So inherently, and you face challenges in modeling the load flow as well, right? So the AC-DC distribution system, you need to model the converters as well to be able to model the load flow, right? So this is something that you face, and why I'm saying that is because let's say, right? I to A by I want okay, let's not discuss it over here. Let's discuss over here. Let's say I want to do this forward backward sweep for this AC-DC distribution system, right? But let's say between these two buses there is a converter. There's a converter present, right? It converts voltage from one voltage level to another voltage level. So when it is present, I can't simply write what is this voltage. This is not possible. So what we do is we write something like this. With presence of uh, converter, we write it V2 is equals to, if let's say there is a buck voltage buck converter present, we write it like dV1 minus of I12 Z12. So we lump the line and we change the buck level as well, right? And the buck level is dV1. So that is what essentially we try to do. So that is why this modeling of DGs or modeling of this converter is essential for your AC-DC distribution system to be able to use forward backward sweep, right? So this becomes complex in AC-DC distribution system, but not that much complex in AC distribution system because you can straight away use FBS, forward backward sweep, inherently. AC-DC distribution system has fewer elements. No. Available load flow methods for transmission systems can also be applied to AC. No, because in distribution systems you have high R by X ratio. So the correct answer is only A. So what are the main features of power flow control strategy? A, peak load reduction. Correct. You need peak load reduction. That is why you use PFCS. Next, you have effective control and management. Obviously, by using a power flow control strategy, you are able to manage or provide control over the different resources, right? Increase the lifespan of storage system. Correct, because you are modeling the lower voltage, lower SOC level and higher SOC level, and you are ensuring that you don't move beyond them. So the correct answer is all of the above. Next, the transmission losses in the Indian power system as of August 2013 account for dash. So this is just data taken from instructor slide. I will request you to please watch it, please see the slide, but still I'll give you the answer. The answer is 2%. So you see, this is huge. So transmission losses. So if let's say there is 250 gigawatt of generation, just assuming 250 gigawatt is nothing, right? 250 is I don't even it's not it's not something that is it's 450, but let's assume 250 gigawatt. So that means if you're generating 250, you are giving 5 gigawatt to transmission losses. So you see, this is huge, and you can check online for different countries, and you'll find that surprisingly they are they are generating more, but their losses are well below a certain limit, right? So 2% is huge. Next, identify the correct statements. In PHIL applications, the control signals are of high voltage level, and in CHIL applications, the control signals are of low voltage level. So the control signals, the control signals are modeled using a DSP board or an Arduino, right? So Arduino has how much voltage level? Plus minus 5 volts, right? So it's very low. It's low voltage, right? So, so the control signals are always of low voltage level. So the correct answer is B. In PHIL applications, the complexity of the circuit is less compared to that of no. The complexity increases, right? Because now you have to model a power amplifier and you have to connect your converters and other stuff that you have with that. So I've explained all of this in week 10 and also in week 9. So I would request you to go and watch it. What are the different operating modes of power flow control strategy? So I've talked about it. It's peak, off peak, and isolated. These both are grid connected, and this is when it's isolated. So the correct answer is all of the above. Right. Next, where what are the five regional power grids in Indian power system? So five needed: northern, eastern, southern, northeastern, and western. So the correct answer is A. These are the different RLDCs present in Indian power system. Next, what are the different types of buses in AC/DC system? So we have talked about it in depth, right? So you have slack, you have PQ, you have PV, you have P, and you have V. So it's essentially if you write DCP and DCV. So the correct answer is this one. So you have slack or reference, you have DCP bus, you have PV bus, you have PQ bus, and you have DCV bus. Next question. AC load flow studies refer to the transient state analysis of the power system computing voltages and angles at each buses. So yes, so load flow studies are used to figure out the voltages and angles at at each bus, but these are steady state analysis. So it's steady state. So what do you mean by steady state is that you don't account for the transients that are occurring in the system. That is not something that you use. You take the power flow value, the Q value, PQ values or PV values, whatever are given, but you take steady state values. You don't take transient values because it's not a transient state analysis. Because in transient state analysis, the voltages and the fluctuations are very high. So if the fluctuations are very high, you can't use that to compute voltages and angle, right? Statement B, AC load flow studies compute voltages and angles at each bus. Correct. So you so load flow studies do this only, right? They are used to compute the two state variables, which are bus voltage magnitude and bus voltage phase angle. So the correct answer is A is false, B is true. Right. The last question, statement A. The transmission system has a high R by X ratio. So I said it has a low R by X ratio. So if it's a low R by X ratio, that means if I do just a reciprocal of it, it means it has a high X by R ratio. The distribution system has a low X by R ratio. So it has a high R by X ratio, but a low X by R ratio. So this is also correct and this is also correct. So the correct statement is C. Both A and B are true. Right, so we discussed all of these sample problems. I hope these are enough to solve your assignment. So yeah, so we discussed a lot of things today. I hope that you are able to at least get something out of it. And I hope that you are also ready for your uh, exams if at all you have registered. And if there are any doubts, please feel free to, comment in the YouTube comment section. I will be happy to solve your doubts. I have said that I have said this a lot of times, and sorry, I have said this a lot of times, and please don't be shy. join the classes, be regular. I hope that at least I'm able to, provide at least some knowledge to you, some doubts I could clear. But you have to ask doubts for me to clear. But if at all there are any doubts with respect to the class lectures, because I'm just giving you a brief recap of everything, I hope that you are able to get something out of it. Anyways, I wish you uh, uh, wish you a very good evening the rest of the day, and I'll see you all in our last class next week. So yeah, bye bye. Take care.